Chapter 18.3, the Wilcoxon rank sum test for two independent samples. In Chapter 10, we discuss a hypothesis test comparing two independent samples when the standard deviation of the population were unknown. For example, recall that we compare the average gas mileage for a particular car model with air conditioning on and windows up to the gas mileage for the same model with the air conditioning off and windows down. These parametric tests utilize the student distribution, which requires the population to be normally distributed. When this assumption cannot be made, we can use a non-parametric procedure known as the Wilcoxon rank sum test. The only requirement for these tests are that the data be at least at the ordinal level of measurement and that the shape of distribution for the two populations are similar. More specifically, the Wilcoxon rank sum test determines whether two populations have the same probability distribution based on evidence from two independent samples. In the following sections, we will focus on testing if the medians from the two populations are different. We will examine both the small samples and large sample cases in the following sections. Small sample cases. The small sample case for the Wilcoxon rank sum test is appropriate when n less than or equal 10 for both sample size. I will use the following example to demonstrate this technique. Suppose Sallie Mae, a provider a student loan, would like to determine if there is a difference in the median age of full-time MBA student versus the median age of part-time MBA students. Table 18.12 shows the ages of random sample of 15 full-time and part-time MBA students. This data can also be found in the Excel file MBA student ages.xlsx. The following step will show how to perform this non-parametric test using alpha equal to 0.05. Step 1. Identify the null and alternative hypothesis. The Wilcoxon rank sum test focuses on differences between the probability distribution of the two populations of interest. This is a two-tailed test because we are investigating whether the median age of full-time MBA student is different than the median of part-time MBA student. So the null hypothesis is there is no difference in the median age for FT and PT MBA student. Alternative hypothesis, there is a difference in the median age for FT and PT MBA student. Step 2. Identify sample 1 and sample 2. We will designate the sample with the smaller number of observations as sample 1. We will use the variable n1 and n2 to indicate the sample sizes of sample 1 and sample 2, respectively. For the Sallie Mae example, so sample 1 is the part-time student age, and sample 2 is the full-time student age. For the part-time student, n1 is equal to 7. For the full-time student, n2 is equal to 8. If the two samples have an equal number of observations, it does not matter which group you designate as sample 1. Step 3. Sort all of the data value from low to high and rank them. Table 18.13 shows the combined data for both samples sorted from low to high values along with their corresponding student types. In addition, each value is ranked from 1 to 15 from lowest to highest. The student who is 22 years old is the youngest in table 18.13 and is assigned rank of 1. The 23 years old student is the second youngest in the table and is assigned rank of 2. Notice that there is a tie between the two students who are 32 years old because these ages are the 10 and 11 rank value. We assign both of their rank the average of 10 and 12, which is 10.5. Step 4. Determine the test statistic W. The test statistic W equals the sum of the rank for sample 1. If the sample sizes are equal, either sample can be used to calculate W. Because the part-time student represents the smaller sample size, so W is equal to 4 plus 8 plus 10.5 plus 10.5 plus 13 plus 14 plus 15 equal to 75. Step 5. Determine the upper and lower critical values for the Wilcoxon rank sum test. The upper and lower critical values for the Wilcoxon rank sum test are used to identify the rejection region for the null and alternative hypothesis. These values can be found in Table 1 in Appendix C at the end of this chapter on page 18.48 and also in Table 18.14. Using n equal to 7 and n equal to 8, the lower and upper critical values are 39 and 73, respectively. These values are highlighted in Table 18.14. Step 6. Compare the test statistic to the critical values. Table 18.15 summarizes the decision rule for the Wilcoxon rank sum test. Because W equal to 75, it is greater than the upper critical value, or 73, so we reject the null hypothesis. Hopefully, the logic of the Wilcoxon rank sum test makes sense to you. If null hypothesis is actually true, the distribution for the two populations are identical. Under this condition, you would expect the sum of rank of the two samples to be fairly close to one another. If the null hypothesis is not true, the distribution for the two populations are different from one another. This should result in the rank sum of one sample being relatively smaller than the other. When the two rank sums are relatively far apart, we have the tendency to reject the null hypothesis. Step 7. State your conclusion. Because we reject the null hypothesis, Shelley May can conclude that there is a difference in the distribution for the two populations, that is, the median age for full-time MBA students is different than the median age of part-time MBA students. It appears that full-time students tend to be younger than part-time students. We can also perform a one-tailed Wilcoxon rank sum test with the small sample case. The only difference between the one-tail and two-tail procedure is using the proper table to identify the lower and upper critical values. Large sample case. The large sample case of the Wilcoxon rank sum test can be used when n1 greater than 10 and n2 greater than 10. Under this condition, the test statistic can be approximated by the normal probability distribution using equation 18.8, where ZW is the test statistic for the Wilcoxon rank sum test. W is the sum of rank for sample 1. N1 is the size of sample 1. N2 is the size of sample 2. Nt is the N1 plus N2. We will use the following example to demonstrate the large sample case of the Wilcoxon rank sum test. Judicial states are states in which a mortgage lender must get the approval of a court before foreclosing on a home. Non-judicial states have no such requirement. Suppose the Federal Housing Finance Agency, or FHFA, would like to determine if the median number of days to foreclose on a home in non-judicial state is less than it is in judicial states. This data can also be found in the Excel file foreclosures.xlsx. Let's test this hypothesis using the large sample case for the Wilcoxon rank sum test when alpha equal to 0.05 using the following step. Step 1. Identify the null and alternative hypothesis. This is a one-tail or lower test because we are determining if non-judicial states require less time to foreclose on mortgages than judicial states. Null hypothesis. The median number of days to foreclose in non-judicial state is not less than judicial state. Alternative hypothesis. The median number of days to foreclose in non-judicial state is less than judicial state. Step 2. Identify sample 1 and sample 2. Sample 1 is defined as the sample with the smaller number of observations. Therefore, we define sample 1 equal to non-judicial state where N1 equal to 11. Sample 2, judicial state where N2 equal to 122. Step 3. Sort all of the data value from low to high and rank them. Table 18.17 shows the combined data from both samples sorted from low to high values along with the corresponding state type and rank. Step 4. Determine the test statistic, ZW. Before we determine our test statistic, we first need to calculate W, which equals the sum of the rank in sample 1, or the non-judicial state. W is equal to 2 plus 4 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 14 plus 19 equal to 102. Using n equal to 11 and n2 equal to 12 and nt equal to n1 plus n2 equal to 11 plus 12 equal to 23, we can now calculate the test statistic using equation 18.8. Step 5. Determine the critical values for the Wilcoxon rank sum test. Because the large sample case test statistic from equation 18.8 follows the normal probability distribution, the critical value for this one-tail or lower Wilcoxon rank sum test is Z alpha equal to minus 1.645. using alpha equal to 0.05. Step 6. Compare the test statistic to the critical value. Table 18.18 summarizes the decision rules for the large sample case for two-tailed and one-tailed hypothesis. Because CW equal to minus 1.85 and H less than Z alpha equal to minus 1.645, we reject the null hypothesis. Step 7. State your conclusion. Because we reject the null hypothesis, the FHFA can conclude that the median number of days to foreclose and non-judicial state is less than it is in judicial states. 18.4. The Wilcoxon sign test for two dependent samples. Back in Chapter 10, we introduced dependent samples in which each observation from one sample was related to an observation from the other sample. A hypothesis test for comparing two dependent samples using the student T distribution was demonstrated. This parametric procedure works only when both population samples have normal probability distribution. When this assumption cannot be verified, we can use a non-parametric procedure known as the Wilcoxon sign rank test, which does not have a normal distribution requirement. To demonstrate the Wilcoxon sign rank test, I'll use an example from Chapter 10. Rockstar is an energy drink distributed by PepsiCo and sold in grocery stores. Josh is a PepsiCo account manager for 9 different stores and is responsible for product sales and inventory. Josh would like to test the hypothesis that placing the product on the ends of aisles result in more sales than placing them on middle aisle shelves. For each of his 9 stores, Josh displayed the drink on the end of aisle for 1 week and then on middle aisle shelf the following weeks. Table 18.19 shows the number of units of the drink sold in each location at each of the 9 stores. The data can also be found in the Excel file rockstar.xlxx. I hope you recognize these samples are dependent because each pair of sales data is collected from the same store. Using alpha 0.05, let's perform the Wilcoxon sign rank test by taking the following step. Step 1. Identify the null and alternative hypothesis. This is a one-tail test because we are investigating if end aisle sales exceeds middle aisle sales. Null hypothesis: end aisle sales are equal to or less than middle aisle sales. Alternative hypothesis: end aisle sales exceeds middle aisle sales. Step 2. Identify sample 1 and sample 2. For a one-tail test, define sample 1 as the sample that the alternative hypothesis predict will be larger. Because our Rockstar example is a one-tail test and the alternative hypothesis predicts that end aisle sales will exceed middle aisle sales. Therefore, sample 1 is equal the end aisle cells, and sample 2 is equal the middle aisle cells. For a two-tailed test, the choice for sample 1 is arbitrary. Step 3. Calculate the sign rank differences. Table 18.20 shows the sign rank differences and sales for each of the 9 stores from our sample. I realize this table has a lot of information, so let's break it down column by column. Column 1, 2, and 3 in Table 1820 simply display the original data shown in Table 18.19. Notice that I have labeled Sample 1 as the end aisle data and Sample 2 as the middle aisle data, as discussed in the previous step. Column 4 is the difference in the two samples. Define the difference as Sample 1 minus Sample 2. Column 5 is simply the absolute value of the differences seen in column 4. Column 6 is the rank of each absolute difference for all 9 stores. Notice that store 5 and store 9 both have the lowest rank. We assign both of these stores the average rank of 1 and 2, which equal to 1.5. Also, store 4 has the largest absolute difference, or 35, and is assigned the highest rank, which is 9. Column 7 is the sign rank for each store, and it is either a positive rank, or R+, or negative rank, or R-. Store 1 has a negative difference, -8, in column 4 because the middle aisle sales were more than the end aisle sales. We therefore place it rank 4 from column 6 under the negative rank column. Store 2 has a positive difference, or 13, in column 4 because the end aisle sales were more than the middle aisle sales. We therefore place its rank of 5 from column 6 under the positive rank column. Finally, we sum the positive sign rank column, or 36.5, and the negative sign rank column, or 8.5. Step 4. Determine the test statistic T. The test statistic for one-tailed Wilcoxon sign rank test, T, is the sum of the negative sign rank, or R-, in Table 18.20. For our Rockstar example, T is equal to 8.5. In order to reject the null hypothesis, we need to establish that end aisle sales in our sample are significantly higher than middle aisle sales. Rejecting the null hypothesis would require most of the sign rank to be in the R+ column in Table 1820, and very few sign rank would be in R- column. Therefore, the smaller the test statistic, the more likely that we will be able to reject the null hypothesis and establish that end aisle sales are higher than middle aisle sales. Step 5. Determine the critical value for the Wilcoxon sign rank test, T alpha. The critical value for the Wilcoxon sign rank test, T alpha, is used to identify the rejection region for the null and alternative hypothesis. This value can be found in Table 2 in Appendix C at the end of this chapter. on pages 18-48 and 18-49, and also in table 18.21. For a one-tailed hypothesis test with alpha equal to 0.05 and n equal to 9, we have 9 stored in our sample, T alpha equal to 8. Step 6. Compare the test statistic to the critical value. Table 18.22 summarizes the decision rule for the Wilcoxon sign rank test for two-tailed and one-tailed hypothesis. Because T equal to 8.5 is greater than T alpha equal to 8, we fail to reject the null hypothesis. Step 7. State your conclusion. Because we fail to reject the null hypothesis, Josh cannot conclude that end aisle sales exceeds middle aisle sales at his store, even though most of the sign rank were positive in table 18.20. The sum of the negative sign rank was not low enough to warrant rejecting the null hypothesis. This leads to an interesting point. Back in chapter 10, when we first introduced this example, we made the assumption that both population, end aisle and middle aisle, follow the normal probability distribution. We then proceeded with the t-test for dependent samples and were able to reject the null hypothesis using alpha equal to 0.05. Figure 18.3 shows the Excel output for this test with a p-value equal to 0.0303. Now, when we apply the Wilcoxon sign rank test to the same data and use the same value for alpha, we fail to reject the null hypothesis. Why? This scenario emphasizes the point made at the start of the chapter. All S being equal, the same sample size, same level of significance, and so on, the parametric procedure will provide a higher probability of correctly rejecting the null hypothesis than the non-parametric procedure will. If we can verify that the population are normally distributed, and t-test should be used for this example. If we cannot confirm that the population are normally distributed, the Wilcoxon sign rank test is a better choice, even though we are not able to reject the null hypothesis in this particular example. Finally, the two-tailed Wilcoxon sign rank test is handled a little differently than the one-tailed Wilcoxon that we just discussed. Designating which data should be labeled sample 1 and which data should be labeled sample 2 is completely arbitrary. The test statistic T is the smaller of the sum of the negative sign rank R minus and the sum of the positive rank or R plus. Thank you.